This transmission provides nearly twice as many drive ratios as other transmissions that are far more complex than this one. So let's look inside. At the input end, we have an input spline and a gear, and that gear drives two other gears which drive a spline shaft. The spline shaft drives some indexed registered cluster gears.
Regarding those shafts that run up the center of the cluster gear or counter gears, whatever you want to call them, those were made from gear stock, and the gear stock is 4140 alloy. It's cold rolled and work hardened. It has a very, very nice finish. It's machined down to give an approximation of a spline shaft for the purposes of this prototype. The gears that ultimately slide on and run on this the spline shaft, the dimensions for the internal spline, 3 gears were made. One with nominal dimensions, another one with dimensions that were a little bit larger, and one with some dimensions that were a little bit smaller. The one that had the best fit, those dimensions were transferred over to the other gear designs.
Taking a second view of this, you can see the other cluster gears up here. You'll see some radial dog clutch features on the interior of this gear. Complementary to those are 2 output members. They're 2 couplings that also have radial dog clutch features. This is a coupling pair, and they're complementary and will drive against or will be driven by these features. Each coupling conveys its motion and torque down to the output end. This coupling pair can translate axially along these splines and be positioned just about anywhere within a range and transmit their torques and motions to the sleeve and shaft. They move together as a unit axially, but they are rotationally independent. Output or ratio gears mount up the middle and are driven by and supported by and located by the cluster gear pair. Both of the couplings can engage in one gear, or one may be in one gear and the other in another gear, or once again both in the same gear.
Taking a little closer look at the dog clutch pair, you can see them here. The features on the dog clutch features themselves, they're shown as kind of sharp here. Actually, in reality, they're a bull nose here and here, and in fact on all of them. As well, the gears that run up the middle, the ratioing gears I call them, those mating features also are bull-nosed here and here and on the back side also.
Now we can add in the rest of the output or ratioing gears or ratio gears, as you can see, and there is also a reverse gear, which is immediately adjacent what you would call first gear. Reverse gear is driven by a pair of idlers or reverse idlers, as you can see. We can look at all this with respect to some parts that have already been built. What you're looking at here are some features that I call train wheels, train tires, whatever, that help to keep the ratio gears perfectly centered between the 2 cluster gear sets. To get a little better view of reverse gear, we can see it running. In this case, reverse gear drives indirectly off of first gear instead of off of the cluster gears. Since you've seen the gears rotating, now let's look at a view up the center. You can see reverse gear in the foreground here, and then first gear and all of the other stages. And you can see that the relative motion between immediately adjacent stages is fairly low. And that's what makes it possible to shift as the coupling pair moves axially from position to position. If both of the couplers are in the same gear, both this sleeve and the shaft are spinning the same speed. But if the coupling pair is straddling two gears, then the sleeve and the shaft are spinning at two different speeds. Well, this is where the number of drive ratios practically doubles. And that is because they get combined via an integrator. It looks like a differential, but it's not. A differential takes one input and splits it into two differential outputs. An integrator takes two inputs and generates an integrated output. And that is how the number of ratios in this thing practically doubles, I'm going to say in real time, as it slews through the various ratio selections.
It would be a little difficult for me to actually make the beveled gear integrator as you see shown in the CAD. But what I can do is make the spur gear equivalent of that, and that's based on some standard parts that are readily available. For instance, this gear, it requires 6 of them. I got 1, need 5 more. This bushing, which is an iron bronze bushing, has very, very good load carrying capability. I have those. And this internally splined flanged adapter, and obviously I have that, only need 1. And now you see all of those parts shown in the CAD.
Let's look at a more interesting view of the spur gear integrator. We're looking through the carrier in some places, which is the transparent looking thing, and we can even get a clearer view if we remove the carrier altogether. Now you can see the gear that ties into that sleeve, central sleeve, and the gear that ties into the central shaft. And everything's mixed together. There's a lot of tooth contact, which is a good thing. Not only are 11 output drive ratios provided by only 6 gear ratios, I'd like to show you an added refinement. What I've done is rotated the transmission on its axis to show you what I call the non-linear ratio spread. This curve passes through the pitch diameters where the ratio gears and the cluster gears mesh. Notice that the slope is shallower toward what would be the upper 4, 5, or 6 gear ratios in this transmission, and a little steeper toward first gear. This is in the cruise range, which is where you're going to want to more closely match your engine's performance and your vehicle's driving condition in order to optimize your fuel economy. Now you can more clearly see that this curve passes through the pitch diameter. There's some additional support that could be applied, and that is by the use of saddle bearings. question now arises, how do you control something like this? Well, since you only have one shifting element, kind of leaves the field wide open as far as control methods. One is servo hydraulic, where you have a pump, an accumulator, a servo valve, a controller that responds to operator input, some sensors. Anybody who knows servo hydraulics knows how quickly uh, something like this can be positioned, and with the speed that the accumulator provides, control would not be an issue. So now there's a seal here for rotational only, a seal here for rotation and axial movement, something that looks like a piston ring between this single shifting element and this cylinder wall, and a spline seal. So now you have two confined spaces. You treat it just like a double acting hydraulic cylinder. Another way to do it is with a cylindrical cam. That would involve the cam follower, a rotary actuator with an encoder or resolver, again with a control unit responding to operator input. Or you can use purely mechanical means. What follows now is a supplemental to the current project. I'm going to show you a refinement in the design of these features. Let's go ahead and look at that. Here you see this single shifting element with a pair of features and what looks like a piston and a groove for a piston ring. You can see on the interior here there's a ball bearing race and a bunch of ball bearings. We can take a look at it the other way and you can see complementary race. We want to look at this interface right here. You can see that with these radiuses or shapes, it takes away a little bit from the face width. Let's take a better look at the interface from another view. This is the coupling interface right there. That is where contact stresses will occur. We saw what the face width was. We're only going to analyze this based on these interfaces and the torque that they're going to be able to take. This analysis looks at the torque limits and the contact stresses for a carbon steel that's used typically for gears and shafts. These numbers are designations for the same carbon steel given by other countries. Any analysis is highly dependent upon material heat treatment, surface hardness conditions. So I'm just using some published data. In this part of this little analysis, we want to determine what kind of forces are required to shear these radial dog clutch features off. There are 4 of these features per coupling, and there are 2 couplings. So we have 8 of these features. First, to determine the forces required, we need to know the area of the shear plane. One dimension is 0.423, and these are all 1/4 of an inch thick. So we multiply these 2 numbers together, we end up with the area of the shear plane. Using this number for determining shear forces, we see that the force required to shear off this feature is 8,617 pounds. The torque required to produce that force at this radius into feet, and we end up with 1,094 foot-pounds of torque to shear off one of these. We have 8 of them, so that translates into 8,755 foot-pounds of torque for the coupling pair. Now, that is a very big number, but that's okay. We're trying to get an estimate as to what limits what. Next, we look at the static contact stresses at the coupling interface, which is where these two are pushing on each other, and the relative forces are in these directions. We need to know what the area of the principal contact plane is. We know from looking through that transparent gear earlier One of the dimensions is the face width, and it's 0.1 inch. We have a height of 0.180. So the area is those two numbers multiplied together, so we have a contact area of 0.018 square inches. We know that excessive coupling loads will result in deformation and displacement of material if the yield point of the core material supporting the coupling faces is exceeded. Maximum stresses take place at 45 degrees to the principal contact plane. Thus, the limit of our load will be governed by 0.707 of the tensile yield, which turns out to be 82,295 psi. So the maximum allowable load is our surface area times that number. So the material at each interface will fail under a load of 1,481 pounds. There's 8 of these coupling interfaces per coupling pair, and that translates into 11,850 pounds. So taking those numbers and looking at it in terms of foot-pounds, the coupling pair can transfer torque up to 1,505 foot-pounds. Now, considering that the output of the transmission usually will drive an output differential whose ratios can range from 2.5 to 4.0, that becomes a multiplier for this number. Nonetheless, considering the forces and stresses in shear compared to the forces and contact stresses, it can be concluded that contact stresses drive the torque carrying limit of the coupling pair.